my dear students. Hope you all are fine by the blessings of God and you all are maintaining social distancing. So now it's the high time when you can start studying, as you have enough time in your hand. And before starting the chapter, I hope that you all have the required things with you. Today I will start the chapter 2, which contains work, energy and power. Today I shall discuss the part, very important part, that is the work. You know that in our daily life several times we use the word work, and we use it for various activities such as writing, swimming, eating something, etc. But what is it actually? According to physics, what is it? Before starting that, I should say, in your syllabus, the definition of work, mathematical expression of work, some special cases, work done by the force of gravity, these 4 parts are there. So these 4 parts, the important parts, I will discuss now. So I finished with what is work actually. To know that, we should see this one. Here you can see one block. Okay, that block is pushed by a force F, and whenever the force is applied on the block covers some distance. Okay, so let me assume the block was in the position A and it moves to the position B. That is the distance. And we can say in physics the term work is used which is related to displacement produced by a force. Okay, so here the force F is applied on the block, and this amount of force is able to move the block. Okay, so from here we can say work is said to be done only when the force applied on a body and makes the body move along the direction of force. Now you please note one thing, that the force F and the displacement S both are vector quantities, but their product, that is the work, is a scalar quantity. Okay, so work can be expressed as the dot product or scalar product of force and displacement. Okay, now when work is done and when work is not done, just use your brain and try to say when work is done, when work is not done. Here you can see that Atlas holds up the earth, but he doesn't move. So does he do any work? What's your opinion? I know? No. The answer will be no. Why no? Because to do any work there must be some displacement. Okay, but Atlas is in his position only. He is not moving from his position, so his displacement is 0. That's why he has not done any work. Okay, so here only this man, you can see the man, this man is picking up a tray from ground, or you can say any table, and he must do some work, but with the tray, while he is moving around the room, does he do any work? Let's think. Can you say? Yes, whenever he is working, his displacement and the force is obviously perpendicular to each other. As these two are perpendicular to each other, so the work done is equal to 0. By the next slide, conditions for the work done by a force is 0. what are the conditions for the work done by a force is 0? So condition 1, when there is no displacement, that is S equals to 0, then the work done is 0, and when the displacement is normal to the direction of the force, that is theta equals to 90 degree. I have shown you both the cases when there is no displacement. Okay, now let's see if we have any other concept of work done. See, what is work done? If you see Newton's second law, gives us F equals to ma, that is force equal to mass into acceleration. The work done by a force on a moving body is equal to the increase in its kinetic energy. So what is work done? Change in half mv square. Half mv square is the expression of kinetic energy. So work done equal to change in kinetic energy. If this equation F equals to ma, it is a vector equation. Clear? So from Newton's second law of motion, you know F equal to ma, and you also know W equal to Fs or Ft, whatever. And equation of motion, from equation of motion you can clearly set up that S equal to v square minus u square by 2a. So what W becomes? W becomes F into S, that is ma into S means v square minus u square by 2a, which gives us half m into v square minus u square, that gives us change in kinetic energy. So directly I have written here the work done is given by the change in kinetic energy. So you have learned a new concept. It is called as the work energy theorem. This is known as work energy theorem. Now come to the next part, that is the mathematical expression of work. Now the mathematical expression or work done is a dot product of force and displacement, as I have said earlier. So W equal to vector F dot S, vector S, that gives us Fs cos theta. W equals to Fs cos theta. What is theta? Theta is the angle between F and S. So now my question is how to determine the amount of work done. The amount of work done can be determined in two ways. Number one, by finding the component of displacement of the body in the direction of force. So we have to find out the component of displacement. Okay, so obviously if the displacement is S, there must be two components. Here you can see the one block and one inclined plane. Whenever a force is applied on a block, it changes position. So there must be some displacement. So if the displacement is S, the AV here gives us, because the displacement S makes angle theta with the horizontal, so AB becomes S cos theta. Clear? So this is one component of displacement. If we find out the component of displacement from here, okay, and the next part, by finding the component of force in the direction of displacement. Here also we can find out by finding the component of force in the direction of displacement. We can see if force, the amount of force is given, that is if, at the component there are also two components, I told already, F cos theta and F sin theta. So we can see here from the bottom part, F cos theta is given to the body, okay, and the body displaced from its original position. Clear? That the work done W equal to NA multiplied by AC. Okay, so we can give NA multiplied by S, as AC is given by S. So if we see the right angle triangle, that is PNA, from here we can say that NA equal to PA cos theta, that is the F cos theta. Okay, so W equal to F cos theta into S. From there we can find out the mathematical part of work done. Okay, so from here next part we will say that is the positive work done and negative work done. But before that, I should clearly say that the work done is equal to the product of magnitude of force, the magnitude of displacement, and cosine of the angle theta between the direction of force and displacement. Clear? Now the first part, that is the positive work done. When work done is said to be positive, very important part, when work done is said to be positive. So if the angle between force and displacement is acute angle, that is lies between 0 degree to 90 degree, the cos theta becomes positive. Okay, you can take any of the values of cos theta between 0 to 90 degree, it will give us a positive sign. So which signifies when a force and displacement are in same direction, work done is positive. This work is said to be done upon the body, on the body. Work done is said to be done on the body. Clear? Now let's take one example here of positive work done. In a free fall body, suppose the mass is m under gravity, from height y it is falling from A to B. So the force of gravity F, which is equals to mg, is in the direction of displacement. Okay, and the work done by the force of gravity we know already, F equal to Fd. Okay, here d is how much? Y, so it becomes mgy. The work done by the force of gravity is equal to mgy. And let me say about the zero work done or no work done. When the work done is said to be when the force acts in a direction at right angle to the displacement, that is 90 degree, then the value of cos theta will be cos 90, that is 0. So no work is said to be done. Here you can say one man who is lifting up a suitcase and moving forward. So the angle between the force and the displacement becomes 90 degree. So what is the value of cos theta? It becomes cos 90, that gives us 0. So when F is perpendicular to D, that means theta is 90 degree, cos theta 0, so W becomes 0. So work done by the man becomes 0. And the another one which I can say, that is when a body moves in a circular path in a horizontal plane, no work is said to be done. Why? Because centripetal force on the body is directed towards the center of circular path, and the displacement at all instants is along the tangent of the circular path. Okay, that is the normal to the direction of force on the body. So this is, for this reason, is a circular path, the kinetic energy and hence the speed of the body doesn't change although force acts on the body. Is it clear to you? Again I am saying here displacement at all instant is along the tangent to the circular path. Clear? That is normal to the direction of force. And here also the same scenario, F and D becomes normal, that's why the work done becomes 0. Now come to the negative work done. Okay, there are three cases: work done positive, work done 0, and work done negative. So when work done is said to be negative, so work done by a force is negative if the angle between force and displacement is obtuse angle, that is theta lies between 90 degree to 180 degree. So see, from 90 to 180 in this range, cos theta, the value of theta will be something, suppose 120 degree, so cos theta becomes negative. This signifies that when a force and displacement are in opposite direction, work done is negative. This work is said to be negative. Okay, so see, when force and displacement in opposite direction, so anything is coming in your mind? Any example where force is applied in one direction and the body is moving in another direction? What should be a good example? Yes, very good. This is the force of friction, okay, between the body and surface. If there is a frictional force, so in the body is moving forward, friction always working at the backward side. Okay, always against the movement of the body. Clear? And Here also one important part that I have shown you, negative work done. The man is trying to pull up the body from the ground, and when he is pulling up, force is acting upward, okay, but the weight of the body is acting downward. Clear? That is in two opposite direction. Work done becomes negative. Okay, so let's see the unit. So what are the units? See, we will compare the unit of work done with kinetic energy. Why? Because I told you that work done is equal to the change in kinetic energy. It means there must be some relationship. Let me show the relationship. Here the kinetic energy is equal to half mv square. Clear? So what is the unit of m in SI? That is kg. What is the unit of v in SI? That is the v square, means meter square, meter per second. V is meter per second, so v square means meter square per second square. And the what is the unit of F? Newton. What is the unit of D? Meter. So it gives us Newton means what? What is Newton? F equal to ma, mass into acceleration, kg into meter per second square into multiplied by meter. This gives us the same scenario. That is the unit of kinetic energy and unit of work done are same. Kinetic energy, unit of kinetic energy and unit of work done both are kg meter square per second, kg meter square per second square. Is it clear? Now the rest part, that is the work done by gravity. What is the work done by the force of gravity? See, a body, let me take one body of mass m. It is moving down through a vertical height. Suppose this is the starting point, that is the end point. Okay, so this is the distance. From the height it is falling. Either it is directly it may fall, or it can fall through an inclined plane. The force of gravity on the body. What is the force of gravity? I have written here W equals to mg. I have written the force of gravity here. W equals to mg. So here the force of gravity, that is mg, acting vertically downward, and the vertical displacement in the direction of force is h, we can take. Therefore what is the work done here? Work done is given by F cross D. That is, what is mg, F here? Minus mg. Why? Acting downward. Clear? It is done by the force of gravity, that's why it is taken negative. Okay, and what is the distance here? Change in height. So we can now, if gravity is the force, the only force doing work, if gravity is the only force, then what will happen? This special case, that change in mgh equal to change in potential energy equal to change in kinetic energy. Okay, this tells us. So there must be a negative sign. So if I take in one side, so what will come? Change in potential energy plus change in kinetic energy equals to 0. So change in potential energy plus kinetic energy equals to 0. Okay, so change in potential energy plus kinetic energy is 0, means the sum of potential energy and kinetic energy is constant. Again, one new idea comes to our mind, that is the conservation of energy. The addition or the summation, the sum of kinetic energy and potential energy becomes constant. Okay, the sum of kinetic energy and potential energy is constant, becomes constant. Okay, so energy is conserved, we can say energy is conserved. So thank you for your kind attention. Follow the next class.